Hello, I'm Elizabeth Berg, a PhD candidate at the University of Utah. I'm excited to discuss our work with you, Markov chain Monte Carlo regional tomography models of Western North America, findings from Alaska and Southern California. The motivation of this work is to use regional scale deployments, including from the transportable array in Alaska, and networks to create regional scale models of the subsurface with sensitivity from less than 1 kilometer depth in the shallow crust into the upper mantle. We use multiple data sets obtained from teleseismic waves and ambient noise cross correlations through a Bayesian joint inversion, Markov chain Monte Carlo, that enables us to quantify sensitivity and uncertainty. One of our data sets is receiver functions, which resolve teleseism P to S conversions created by structural contrast through deconvolution. This is sensitive to near-station horizontal interfaces, such as the MOHO. We also use Rayleigh wave phase velocities, or the speed of the Rayleigh wave propagating through a medium, from ambient noise cross correlations for shorter periods and from teleseisms for longer periods to obtain sensitivity of 3D subsurface structure within the crust and upper mantle. Our final data set is Rayleigh wave horizontal to vertical, or H/V ratios, which measures the shape, the horizontal motion versus the vertical motion of the Rayleigh wave at a specific station. As shown in the sensitivity kernel, H/V is sensitive to shallower crustal structure compared to phase velocity for the same period. Here's an example of the cross correlations of every station in the TA, cross-correlated with source station DHY, marked as a black star, bandpassed around 16-second period with a reference station, cross-correlograms for ZZ, ZN, and ZE components. Clear retrograde elliptical motion can be seen as the wave collapses onto the source. This is also seen as the wave propagates from the source back out to the receivers. We obtain phase velocities via Helmholtz tomography for longer period Rayleigh waves from teleseismic events, and via iconal tomography for shorter period cross correlations. Here, I focus on the iconal tomography procedure for source station DHY in Alaska. First, as shown on the far left, for 16-second periods, we take the symmetric cross correlations of the ZZ component and use frequency time analysis to obtain phase travel time picks. In the upper center map, phase travel times are shown as determined at each station and interpolated onto the underlying grid. In the lower center map, we see the results of applying the iconal equation, where we take the spatial derivative of phase travel times to obtain slowness and thus velocity for the specific station as a source. Note that Helmholtz tomography is very similar, albeit with an amplitude correction term. We repeat this process for each station acting as a source and stack these to produce our final phase velocity maps. Here are the final phase velocity maps from iconal tomography and ambient noise cross correlations at 10 and 24-second periods, and from Helmholtz tomography through Rayleigh waves created by teleseismic events at 24 and 60-second periods. At 10 seconds, we observe basins, including the Cook Inlet and Colville Basin. At 24 seconds, we observe thicker crust beneath the northern Brooks Range, as evidenced by lower phase velocities. Additionally, at 60 seconds, we see the downgoing Pacific slab evidenced by very fast phase velocities. We are able to repeat this process in Southern California and observe slower velocities in the Los Angeles, Ventura, and Central Valley basins, as well as the Salton Trough. We also observe faster phase velocities in the peninsular ranges. Here we are showing our results from ambient noise cross correlation at 6 and 15-second periods, and from earthquakes at both regional and teleseismic scales at 15 and 50-second periods via Helmholtz tomography. Next, we discuss how to procure H/V ratios. Here we show the cross correlations between source G25K in a sedimentary basin in Alaska and receiver M20K in the Alaskan mountain range for the ZR, ZZ, RR, and RZ components. The particle motion of the Rayleigh wave for receiver station M20K and source station G25K are shown on the right, using the data from the left and shaded accordingly. Clearly, the particle motion is elongated in the vertical direction at receiver M20K, producing lower horizontal to vertical ratios, which we measure as the ratio of the maximum amplitude of the envelope for the corresponding radial and vertical cross-correlograms that create the particle motion, shown here. For the receiver station, this corresponds to ZR over ZZ, maximum amplitude ratio. And for the source station, G25K, this corresponds to RZ over ZZ and RR over ZR. At the source station, G25K, we can see that the particle motion is elongated radially. This produces a high H/V ratio at this basin station, where the contrast between soft sediment and hard bedrock creates an amplified horizontal motion. The result from this analysis for all station pairs is used to obtain the mean H/V ratio at each station for each period. Here we show the results for each station and interpolated onto the underlying grid from ambient noise cross-correlation at 10 and 24-second periods, as well as from teleseisms at 24 and 60-second periods, along with the general sensitivity range at depth. We observe higher H/V ratios in sedimentary basins, including in the Colville and the Cook Inlet. We also observe lower H/V ratios in crystalline rock, such as in the Brooks Range. We repeat this analysis in Southern California, and we show our results at 3, 6, 10, 16, and 24-second periods. We see higher H/V ratios in the Ventura Basin, Central Valley, Los Angeles Basin, and in the Salton Trough. We see lower H/V ratios in the Peninsula Ranges and in the Sierra Nevada Mountains. With increasing period, we see lower H/V ratios overall as our sensitivity moves to below the basin bedrock interface. To review, we have the following data for each station. We have receiver function, phase velocity, and H/V ratios, plotted here along with their uncertainties for station G23K in the northern Ray Mountains of Alaska. We use the Shapiro and Ritzweiler 2002 global diffraction model for our starting model, shown here in red as shear velocity versus depth. In the upper plot, we are showing the upper 10 kilometers, and in the lower, we are showing the upper 150 kilometers of the Earth. Our MCMC inversion is modeled after Shen et al. 2016. Each model consists of a top linear layer, a crustal layer defined by 4 B-splines, and a mantle layer defined by 5 B-splines. This forms our starting model, M0. Bayes' theorem relates the posterior distribution to the prior via the likelihood function. We define the prior for each model parameter based on a range and Gaussian width from our initial model parameters, with details in this table. To visualize this, we have an example of the distribution of the crustal thickness parameter for the prior, transparent and otherwise outlined in orange, and the posterior, which is shaded in blue. In order to form the likelihood function, we must forward model a given shear velocity model via Hermann's computer programs in seismology. Here we show the result of forward modeling the starting model M0 and producing the receiver function, phase velocity, and H/V ratio in red in comparison with the black data and uncertainty. This allows us to calculate the misfit to each data set, and the combined misfit, which is 15 for the starting model M0, is given as the equation S and input into the likelihood function. We walk through this model space using the metropolis law, which uses the likelihood function to determine the probability of acceptance, where we accept a newly generated model if it has higher likelihood, therefore lower misfit, and a certain percentage of the time, we randomly decide to keep a model with higher misfit in order to avoid becoming stuck in a local minimum. For example, from our starting model M0 with a misfit of 15, we can create a new model by slightly randomly perturbing the parameters that make up M0, as previously shown from our prior distribution. This gives M1. M1 has a lower misfit found from forward modeling M1's parameters. So we will again roll the dice and perturb the parameters slightly from M1. This gives a model M2. However, after we forward model and calculate misfit to observe data, we find M2 has higher misfit than M1. We now restart instead from M1, not M2, to again slightly randomly perturb M1 parameters to obtain model M3. We now use model M3 and slightly perturb its parameters to get model M4. Although model M4 has a higher misfit, we may randomly decide to use this model as a starting point anyway in order to avoid local minima. In this case, we slightly perturb model M4's parameters and roll the dice to obtain model M5. We repeat this process, and the set of models produced forms a Markov chain. For our 1D MCMC inversion, we create 12 Markov chains, each starting from our initial model and exploring 3,000 models, walking through the model space following the Metropolis algorithm. This gives a total of 36,000 models. We determine the posterior using a minimum misfit threshold set from the model with the absolute minimum misfit. Next, we will show the result of this inversion at station G23K in the Northern Ray Mountains using only one dataset, phase velocity. This is our result, where each VS posterior model is shown in blue, and the associated forward model result of each posterior model is also shown in blue to compare with the data for the receiver function, phase velocity, and HRV ratios. Again, we only use the phase velocity data to calculate misfit here. And overall, we observe a wide range of posterior models. Note that most of these posterior models do not fit our receiver function or HRV ratio data naturally. If we include the receiver function and phase velocity data together to calculate misfit, we obtain a much tighter posterior distribution of models, but we are still not fitting the HRV data. Additionally, this appears a hair slow near the surface, which is unexpected for station G23K in the Northern Ray Mountains. This, in conjunction with the broader posterior near the surface, suggests we lack sensitivity without incorporating the HRV ratio data. As you can see, if we include all data sets, we obtain the tightest posterior distribution. We fit all the data sets and we capture what we expect near the surface, faster shear velocities for this station. We use this minimum misfit model, shown in white, as our final result at each station. Our final results at each station, interpolated onto the underlying grid, are shown here at 1, 25, 45, and 100 kilometer depths. We observe basin features at shallower depths, including the Colville and Cook Inlet basins. We observe crustal thickness variations at 25 and 45 kilometer depths, including thicker crust beneath the Brooks Range and thinner crust in interior Alaska. At 100 kilometer depth, we observe the cold cratonic mantle, general warm asthenosphere, and the cold downgoing Pacific slab. We are also able to observe uncertainties by the standard deviation of our posterior distribution and observe these at depth to better understand our measurement sensitivity. I'm showing these here for the same corresponding depths for 1, 25, 45, and 100 kilometer depth to show the range of sensitivities. We repeat this for Southern California, and we see low velocities in the Salton Trough, Central Valley, along the coastal ranges, and within the Los Angeles Basin. Overall, we also see higher velocities in the peninsular ranges and in the Sierra Nevada mountains. Additionally, we observe faster velocities beneath the Salton Trough at 25 kilometers depth, suggestive of a shallower moho. We observe faster velocities beneath the Sierra Nevada mountain range at 45 kilometer depth and slower velocities at 65 kilometer depths, which matches previously published studies. Typical of a more traditional inversion scheme, we're able to visualize misfit to our data. We're able to look at this from the perspective of each data set or the combined data set. Here I'm showing the results for Southern California for reference. In conclusion, Markov chain Monte Carlo joint inversion of surface wave, HRV ratio, and phase velocity data from ambient noise cross correlation and from earthquake teleseisms in combination with receiver functions gives important information on the Earth's subsurface. This work is possible only through the knowledge and support from my co-authors, Professor Fanqi Lin, Vera Schultz-Pelcom, and Wei-Sin Shen. Additionally, we thank our many collaborators, including Dr. Hongri Chu, Professors Amir Alam, Kevin Ward, and Yehuda Ben-Zion, and PhD student Kostas Gogas. Thank you for your time and attention. If you would like further information on our 2020 Alaska and 2018 Southern California studies, these are available through JGR Solid Earth and on the IRIS EMC website for both models. Thanks again.